An object from beyond our solar system just passed through. July 1st, 2025, Atlas telescope in Chile spots something moving at 220,000 kilometers per hour. Not a normal speed, not a normal trajectory. Third interstellar visitor ever confirmed. They name it 3I Atlas, and within days, the internet explodes. Alien spacecraft, controlled trajectory, government hiding data. Then a 43-day government shutdown locks NASA silent while the comet swings behind the sun. No updates, no images, just silence. November 19th, 2025, NASA finally holds a briefing. Multiple missions, 20 spacecraft, images from Mars orbit, from rovers on the surface, from solar observatories, from deep space probes. And the verdict? Natural comet. But the details buried in that data tell a stranger story than the headlines admit. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory mission pages published November 19th, 2025, the Arctic preprint server with peer-reviewed astrophysics papers from August through November 2025, and the Minor Planet Center's official orbit determinations. These aren't generic space blogs. These are the technical documents astronomers use to calculate trajectories and measure compositions. Now back to the information. Moving along the border between Serpens Cauda and Sagittarius constellations, near the galactic plane, 3.5 astronomical units from Earth, 4.51 AU from the Sun, speed relative to the Sun, 61 kilometers per second, 140,000 miles per hour. Zwicky Transient Facility at Palomar Observatory had imaged it June 14th. Didn't recognize it. Pre-discovery observations go back 17 days. The Vera C. Rubin Observatory caught it during science validation runs June 21st through July 3rd. Would have discovered it 2 weeks earlier if they'd started sooner. 3 different Atlas telescopes around the world contribute observations. The orbit calculation comes back. Eccentricity approximately 6.1. Hyperbolic, unbound. This object will never return. Trace it backward. The comet clearly originates from outside our solar system. Not from the Oort cloud, not from the Kuiper belt, from interstellar space. Clearly a comet. Active coma, normal composition. 3I Atlas is different. Active like Borisov. But the numbers don't match anything in our records. Means the comet follows a tilted orbit around the Milky Way. Belongs to either the thin disk or thick disk populations. A July 2025 study led by Matthew Hopkins at the University of Oxford runs the kinematics. 68% confidence. 3I Atlas is between 7.6 and 14 billion years old. Based on typical ages of stars in the thick disk, our solar system? 4.6 billion years old. This comet might be older than the Sun, older than Earth, a relic from the early galaxy. Comets have tails that point away from the Sun. Radiation pressure, solar wind, pushes dust and gas outward. This shows a plume extending sunward. An anti-tail. Viewing geometry matters. Earth's line of sight to the comet was only 10 degrees off from the Sun's direction. Edge on view. Correct for that geometry? The sunward extension is 10 times longer than it is wide. A jet pointing toward the Sun. James Webb Space Telescope turns its near-infrared spectrograph on 3I Atlas, distance from the Sun, 3.32 AU. The spectral images span 0.6 to 5.3 micrometers. Results published August 25th in the Astrophysical Journal Letters. Lead author Martin Cordner, NASA Goddard Space Flight Center. The coma is dominated by carbon dioxide, not water. Carbon dioxide to water mixing ratio, 7.6 plus or minus 0.3, among the highest ever observed in any comet, 4.5 sigma above the trend for long period and Jupiter family comets. The nucleus is emitting 129 kilograms of carbon dioxide per second, 6.6 kilograms of water per second, 14 kilograms of carbon monoxide per second, 0.43 kilograms of carbonyl sulfide per second, enhanced outgassing in the sunward direction. Ejected by carbon dioxide and carbon monoxide outgassing, not by water sublimation. This is backward from normal comets. 3I Atlas is undetected in water and carbon monoxide wavelengths. But carbon dioxide? Bright cloud extending at least 348,000 kilometers. Mass loss rate, 70 kilograms of carbon dioxide per second. Water vapor upper limit, 4.5 kilograms per second. The comet was already active at 6.4 AU from the Sun. Normally, comets don't activate until much closer. Water ice sublimates vigorously inside 3 AU, but carbon dioxide sublimates much farther out. This early activity confirms the carbon dioxide dominance. Hydrogen cyanide production rate, 1.5 times 10 to the 25th molecules per second. September 14th, 7 days later, 4.5 times 10 to the 25th molecules per second. Triple increase in 1 week. The comet is heating up. Natural nickel deposits contain both. The nickel concentration rises sharply as the comet approaches the Sun. Pre-discovery observations by Vera Rubin show diameter growth from 13,040 kilometers on June 21st to 18,760 kilometers on July 2nd. 11 days, 5,720 kilometer expansion. By late July, Gran Telescopio Canarias measures the visible coma at 26,400 by 24,700 kilometers, slightly elliptical. Twice Earth's diameter, but that's just the visible dust. The carbon dioxide coma extends over 600,000 kilometers in radius, only visible in near-infrared. At perihelion, the comet loses 5 billion tons of carbon dioxide over 1 month, requires 3 times 10 to the 18th joules of energy. Solar flux at 1.4 AU provides 700 joules per square meter per second. Do the math. Need an absorbing area larger than 1,600 square kilometers? That's a sphere 23 kilometers in diameter, 4 times larger than Hubble's upper limit. For water ice, you'd need 51 kilometers diameter. The numbers don't work for a single intact nucleus. If the nucleus is spinning, why does the coma brightness vary by tens of percent? The jets must be pulsed, periodically active, like a heartbeat. September shows reduction of anti-tail and growth of conventional tail. The viewing geometry changes as the comet moves. The jets are still there, but the angle changes what we see. Side view of the comet structure. The exposure is 3.2 seconds. Spacecraft jitter during observation smears the light by several pixels. The image shows a fuzzy ball, but there's structure, an extension of the glow in the direction of motion ahead of the comet. Position angle, 106 degrees. Projected sunward direction, 115 degrees. Close match, scale of the extension, 3,000 kilometers. At typical thermal speeds of sublimating volatiles, crossing that distance takes 1 day. The plume is extended perpendicular to the sun's direction and ahead of the object. Radiation pressure pushes dust away from the sun. Solar wind slows trailing material. But ahead of the object, perpendicular to sunlight, no natural mechanism easily explains that geometry. NASA can't release data, can't process observations, can't respond to press inquiries. 3I Atlas reaches solar conjunction October 21st. Behind the sun from Earth's perspective, Mars-based spacecraft continue observing. High-rise images sit unreleased. Exceptionally long exposure means the camera can't track the moving comet. Fixed in place during exposure, star trails appear as streaks. The comet is a faint smudge against the streaked background, but visible. 3 sources visible: hydrogen from Mars, interplanetary hydrogen flowing through the solar system, and hydrogen from 3I Atlas, separate signatures. The comet's hydrogen halo is distinct. SOHO mission catches glimpses. Punch satellites designed to study the solar corona capture the comet between September and October. Combined images show the comet's tail as short elongation. Psyche spacecraft, heading to the metal-rich asteroid Psyche, captures 4 observations over 8 hours. Our Europa Clipper, recently launched toward Jupiter's moon, also contributes observations. No ground-based observations possible. Only Mars missions can see it. November 8th. Post-perihelion. Comet reappears in Earth's sky. Michael Yeager, Gerald Raymond, and Enrico Prosperi capture images. Complex tail structure, 4 to 5 tails or jets fanning out in multiple directions. Similar to Comet C 2016 R2, an unusual long-period comet, extremely rich in carbon monoxide and nitrogen, poor in dust. Did not fragment during perihelion passage. Prominent elongation at position angle, 106 degrees. Sunward direction, 115 degrees. Still showing sunward extension. Weaker asymmetry at position angle, 301 degrees. Anti-solar direction, 295 degrees. Conventional tail also present. The comet survived intact. Amit Kshatriya, NASA Associate Administrator, leads. Nikki Fox, Associate Administrator of NASA's Science Mission Directorate, presents the message: 3I Atlas is a comet. All observations consistent with cometary behavior. No technosignatures, no evidence requiring alien technology as explanation. Lucy spacecraft frames, Psyche observations, 20 spacecraft, unprecedented multi-mission campaign, dozens of images, spectroscopic data, photometry, astrometry. High carbon dioxide, low water, unusual for solar system comets, but explicable. Different formation environment, different parent star, different protoplanetary disk chemistry. The forward-directed plume in high-rise images, the mass loss rates requiring 4 times the observed surface area. Fox states clearly, nothing in the data requires technology. All observations fit natural comet models. The speculation is noted and dismissed. Luna tweets November 20th. Had a good conversation with NASA. Images and data release as soon as government reopens. Unfortunately, due to bureaucratic reasons, cannot release until then. Not because the comet threatens Earth, it doesn't. Closest approach to Earth, 1.8 AU, 270 million kilometers. December 19th, 2025. No danger. The exercise is a drill, testing international coordination, precision tracking, orbit refinement, communication between observatories worldwide, dress rehearsal using a safe but scientifically rich target, training for the day a real threat appears. The campaign focuses on comet astrometry, extracting accurate positional measurements from tricky comet images. Fuzzy comets and tails shift the apparent center of light, requires careful technique. Workshops planned, mid-campaign check-in, final teleconference early February 2026, cross-agency collaboration, NASA's Planetary Defense Office, ESA's NEO Coordination Center, United Nations Office for Outer Space Affairs. Same ecosystem that would respond if a truly hazardous asteroid were ever found. Best window for coordinated observations, public telescope live streams expected. Late December through early 2026, comet continues outward, gradually dimming but still tracked by professional observatories. March 16th, 2026, passes near Jupiter's Hill sphere, roughly at Jupiter's gravitational influence boundary. Some speculation about possible interactions, no evidence of any. JWST is scheduled for additional observations in December 2025, after perihelion, composition measurements, jet characterization, mass loading rates, speed measurements. Hubble will continue ultraviolet spectroscopy, monitoring sulfur to oxygen ratio, gas composition evolution, tracking the comet outbound from the solar system, pointing toward and away from the sun, reaching distances of roughly 1 million kilometers, far larger than anything in the official NASA images. Satoru Murata in Japan captures 24 exposures of 60 seconds each with a 0.2 meter telescope. November 9th, 2 distinct tails visible. Frank Niebling reports magnificent large-scale structure. Today's date, November unspecified, late month. Angular extent, 10 arc minutes for the sunward anti-tail jets, 30 arc minutes for the tail away from the sun. At 3 IATLAS's distance from Earth of 326 million kilometers, that translates to 950,000 kilometers for sunward anti-tail jets and 2.85 million kilometers for the outbound tail, 3 orders of magnitude larger than the Hubble July image scale. Tirasak Thaluang in Thailand images it, November 29th at 9:53 p.m. UTC, 0.26 meter telescope. Rayong, Thailand, 2 prominent jets, anti-tail in sunward direction toward lower left, conventional tail toward upper right. The structure is complex, not a simple single-tail comet, integrating its orbit for 10 million years. Using Gaia Data Release 3 stellar catalog, high-quality astrometry and radial velocities. Identifying close passages within 2 parsecs, 93 stellar encounters, 62 high confidence. The comet passed within 1 parsec of 25 known stars in the past 10 million years, 3.3 light years, close enough for gravitational perturbations. Its trajectory has been altered repeatedly. Tracing back to the exact parent star? Impossible. The comet has been traveling billions of years, mixed around with stellar populations, speed changed by gravity assists. If 3I Atlas formed around a thick disk star, the parent star had low metallicity. The protoplanetary disk chemistry was different, perhaps formed close to the carbon dioxide ice line, perhaps exposed to higher radiation levels, perhaps both. Partial obscuration by dust makes quantification difficult, but the ratio exists. Earth has a specific carbon-13 to carbon-12 ratio, set by solar nebula chemistry. If 3 IATLAS shows a different ratio, it fingerprints a different formation environment. Jupiter family comets orbit between Jupiter and Neptune. Long-period comets come from scattered disk or Oort cloud, all formed in the same chemical environment. Same isotopic ratios, same relative abundances of water, carbon dioxide, carbon monoxide. 3 IATLAS doesn't match. It formed somewhere else, under different conditions, around a star billions of years old when our sun was just forming. Cosmic rays bombard objects traveling through interstellar space, high-energy particles, galactic cosmic rays, spallation reactions, chemical alteration, surface erosion, carbon-rich materials transformed into new compounds. Amorphous ice becomes even more disordered. Organic tholins build up. Scientists estimate constant exposure could create a dense dark crust up to 20 meters thick. Alter surface properties, changes how the comet responds to solar heating. But the required surface area still doesn't work. Even with thick crust and unusual composition, sublimating 5 billion tons of carbon dioxide in 1 month at 1.4 AU requires enormous surface area, or requires fragmentation. If the nucleus broke into multiple pieces near perihelion, the combined surface area increases dramatically. Small fragments expose fresh ice. Sublimation rate explodes. Explains the high mass loss. November 11th, images show the comet is still a single body. Hasn't fragmented. Still shows the same sunward extension. Still coherent. If it fragmented, we'd see multiple bright spots. Expanding debris cloud. None observed. The comet survived perihelion intact as a single object. The nucleus is actually 20 to 50 kilometers across. Explains the required surface area, but contradicts the imaging constraints. Hubble resolution should detect a 20-kilometer object at that distance. Pockets of ice facing the sun at specific rotation phases. Explains the 16-hour variability. Explains the jet structure. Requires the active regions to be unusually efficient, higher sublimation rates than standard models predict. Loeb's argument: if you see a plume extending ahead of an object perpendicular to sunlight, what natural process produces that? Radiation pressure pushes dust away from the sun. Solar wind drags material backward. Sublimation creates radial outflow. None of these produces a forward beam, unless the beam is not scattered sunlight, it's emitted light, or reflected light from a directional source, like a thruster exhaust illuminated by its own emission. Loeb's argument: nickel without iron. Natural processes don't separate nickel from iron at the concentrations observed. Industrial alloys do, unless there's some exotic mineralogy in the parent disk that concentrates nickel. Possible, but unusual. Arrives when humanity has the technology to study it. Timing is convenient, unless selection bias. We only detect interstellar objects that pass close enough and bright enough to see. The ones that miss go unnoticed. The trajectory is set by galactic dynamics, not by mission planning. No optical signals, no anomalous thermal emission, no geometric structure, just a fuzzy ball of dust and gas. Comet. It will fade into interstellar space at the same speed it arrived, 58 kilometers per second relative to the sun, 130,000 miles per hour. Unbound trajectory. Eccentricity, 6.1. Hyperbolic escape. Only the third confirmed interstellar object. First was One-Eye Oumuamua 2017. Shape, highly elongated, 10-to-1 axis ratio, tumbling, no visible coma, showed non-gravitational acceleration. Explanations: outgassing, radiation pressure, or Loeb's hypothesis of a light sail. Debate still ongoing. Second was 2I Borisov 2019. Clearly a comet, water-dominated coma, carbon monoxide present. Resembled solar system comets? Less controversial. Fewer heavy elements. Stars had not yet enriched the interstellar medium with supernovae products. The galaxy was more primordial. The comet is a time capsule. Material from that era, preserved in the deep freeze of interstellar space for billions of years, now heated by our sun, releasing its ancient ices. Scientists are sampling material from a protoplanetary disk around a star that might have formed 10 billion years ago. No other way to do this. Can't visit other star systems, can't sample their comets directly. Interstellar travel is science fiction, but interstellar objects come to us. Occasionally, rarely, 3 confirmed in 8 years. Estimates suggest one interstellar object larger than a few hundred meters is always within the solar system at any given time, but most are too faint or pass too far away. We only detect a tiny fraction. The Vera C. Rubin Observatory will change that. Legacy Survey of Space and Time. Begins full operations 2025 or 2026, 10-year survey. Entire visible sky every few nights. Expected to discover tens to hundreds of interstellar objects per year. 3I Atlas is a preview. Rubin will find objects like this routinely. Smaller, fainter, faster. Some will be comets, some will be asteroids, some will be fragments. Some might be other things. A fantastic opportunity to test models on something brand new and possibly ancient. Natural origin, no aliens. The data said, comet with features we don't fully understand. High carbon dioxide, sunward jets, complex structure. Ancient age, thick disk origin, material from a different chemical environment. Survived billions of years in interstellar space, crossed galactic distances, entered our solar system by chance, passed within observable range, and we watched. 20 spacecraft across the solar system coordinated observations. Hubble from Earth orbit, JWST from Sun-Earth, L2 point, TESS from Earth trailing heliocentric orbit, Sphere-X from polar low Earth orbit, SWIFT from low Earth orbit, MRO from Mars orbit, MAVEN from Mars orbit, Perseverance from Mars surface, Stereo A from solar orbit leading Earth, SOHO from Sun-Earth L1, Punch from solar orbit, Lucy en route to Jupiter Trojans, Psyche en route to asteroid Psyche, Europa Clipper en route to Jupiter, Parker Solar Probe in close solar orbit, plus ground-based observatories, Gemini South, Very Large Telescope, Keck, Nordic Optical Telescope, James Clerk Maxwell Telescope, Grand Telescopio Canarius, 2-meter twin telescope, amateur astronomers worldwide. The dataset is unprecedented. Spectroscopy across ultraviolet visible, near-infrared, mid-infrared, photometry in dozens of filters, polarimetry, astrometry, high-resolution imaging, time series observations tracking evolution, composition measurements, outgassing rates, nucleus size constraints, coma structure mapping, tail morphology, jet identification, isotopic ratios, dust grain properties. Dozens already on ARXiv, more submitted to journals. The November 19th NASA briefing was the first official multi-mission summary, but the detailed scientific analysis will continue for years. Each dataset reveals new features. Each measurement refines models. Each observation constrains possibilities. Hubble's August 20th constraint puts the diameter between 440 meters and 5.6 kilometers, most likely under 1 kilometer, but mass loss calculations suggest otherwise. The sublimation physics are straightforward. Carbon dioxide ice requires 600 joules per gram to sublimate. Over 1 month, near perihelion, losing 5 billion tons means 3 times 10 to the 18th joules total energy. The sun at 1 point, 4 AU provides 700 watts per square meter. Convert to joules per second, multiply by seconds in a month. The absorbing area must exceed 1,600 square kilometers. That's a circle with radius 22.5 kilometers, diameter 45 kilometers, 10 times larger than Hubble's upper limit. The disconnect is severe. Maybe the nucleus is surrounded by optically thick dust that obscures its true size. The brightness comes from the brightest pixel in Hubble images. If dust clouds the nucleus, the actual solid body could be much larger. Problem: the images show a relatively clear central condensation, not a completely obscured center. Second explanation: the comet is highly porous, 90% void space, low density, like aerogel, more surface area per unit volume, higher sublimation efficiency. Problem: comets aren't that porous. Typical densities range from 0.5 to 1 gram per cubic centimeter. Even at maximum porosity, can't reach the required area. Third explanation: the active fraction is 100%. Every square centimeter of surface is sublimating. No inactive crust. Problem: no comet shows 100% activity. Typical values: 1 to 20% of surface actively outgassing. Fourth explanation: the sublimation rate per unit area is far higher than models predict. Perhaps the carbon dioxide ice is in an unusual state. Perhaps radiation processing created highly volatile surface layers. Perhaps the thermal conductivity is anomalous. Problem: requires physics that contradicts laboratory measurements of ice sublimation. Fifth explanation: fragmentation. The nucleus split into multiple pieces, not visible as separate objects because they're close together. Combined surface area of fragments exceeds single body area. This matches observations of other comets. Comet Shoemaker. Levy 9 famously fragmented into 21 pieces before impacting Jupiter. Comet 73P Schwassmann-Wachmann. 3 broke into multiple fragments. Comet C 2019 Y4 Atlas disintegrated completely in 2020. Fragmentation is normal for comets under stress, perihelion passage, stresses comets, thermal gradients, centrifugal forces during rotation, internal pressure from volatile sublimation, weak cometary nuclei fracture. The November 11th image showing single body structure doesn't rule out fragmentation. If fragments are close together within a few nucleus diameters, ground-based images can't resolve them. They appear as one fuzzy blob. Only high-resolution space telescope imaging near perihelion could confirm or rule out fragmentation. No such observations exist. Mars-based imaging occurred before perihelion when the comet was still farther out. Post-perihelion imaging from Earth shows the comet too distant for nucleus resolution. The fragmentation hypothesis is testable. If 3I Atlas split into pieces, the trajectory will show perturbations. Each fragment has slightly different velocity. The center of mass trajectory stays on the predicted path, but individual fragments diverge. Over months, the separation becomes observable. Astrometry from December through March 2026 will test this. If multiple position measurements show the comet deviating from predicted orbit, fragmentation is confirmed. If the comet tracks perfectly to predictions, it's still a single body or fragments too close to separate. Measured in meteorites, terrestrial samples, planetary atmospheres, set by processes in the solar nebula 4.6 billion years ago. If 3I Atlas formed in a different stellar environment, the ratio should differ. JWST detected the carbon-13 band. Tentative detection: the line is partially obscured by other spectral features. The preliminary ratio is close to solar. within error bars, but error bars are large. More sensitive observations are needed. If future measurements show definitively solar-like ratio, it constrains formation conditions. Maybe thick disk protoplanetary disks have similar chemistry to our solar nebula. If measurements show a different ratio, it fingerprints a different environment, confirming the comet formed in truly alien conditions. JWST analysis suggests grains smaller than 1 micrometer. Amorphous ice. Fine grains sublimate efficiently. Large grains take longer to heat through. The small grain size means the water ice was recently ejected from the nucleus, not ancient material from the surface. Fresh ice fragments blown off by carbon dioxide outgassing. The composition becomes stratified. Carbon dioxide sublimates directly from the nucleus surface. Water ice ejects as solid grains. Those grains drift outward for thousands of kilometers. Then they heat up and sublimate, creating a secondary water vapor source far from the nucleus. This geometry explains why the water emission is distributed differently than carbon dioxide. Carbon dioxide peaks at the nucleus. Water peaks in an extended halo, 2-component coma. Never seen before in solar system comets at this clarity. By December 19th, 3I Atlas will be at closest approach to Earth, 1.8 AU, 270 million kilometers. Multiple observatories will target it. Best opportunity for spectroscopy. Best geometry for imaging. Best time for detailed characterization. The comet will be outbound from perihelion, already heated, maximum activity, jets fully developed, tail extended, then it fades. By late 2026, it will be beyond 5 AU, too faint for most instruments. By 2027, gone, back to interstellar space, traveling for another few million years until the next stellar encounter, maybe passing within light years of another star system, maybe being observed by someone else, or maybe just drifting, silent, cold, alone. Radiation processing alters surface chemistry over billions of years. Comets can survive interstellar journeys intact. Ancient material preserves isotopic signatures. Jets can display complex geometry. Polarization properties reveal unusual dust. Nickel can be present without iron in specific conditions. Observing campaigns can coordinate globally. International cooperation works. Data sharing advances science. Bureaucracy delays discovery. What don't we know? Exact nucleus size, actual fragmentation state, detailed jet mechanisms, interior composition, isotopic ratios beyond carbon, organic molecule inventory, dust grain mineralogy, formation location, parent star identity, trajectory perturbations over billions of years. How many more like this exist? Whether Rubin will detect hundreds or thousands. What else is out there traveling between stars? Ancient, unusual composition, survived perihelion, currently observable, outbound trajectory, never returning, one of perhaps billions in the galaxy. We happened to see this one. We studied it with every tool we have. We learned what we could. Now it leaves. In 3 years, it will be undetectable. In a million years, it will be light years away. In a billion years, it might pass through another solar system. Maybe someone else will see it. Maybe they'll wonder where it came from. Maybe they'll calculate its trajectory. Maybe they'll find it points back toward a small yellow star in a spiral arm. A star that had a species that watched this comet pass for a few months in their 21st century and argued about what it meant. Composition measurements, images from Mars, a comet from somewhere else, older than Earth, passing through, observed, measured, documented, now leaving. The multi-mission briefing explained what we saw, not what we wanted to see. What the instruments recorded, what the math supports, what the physics allows, a natural object from an ancient star system, carrying ices that froze billions of years ago, releasing them now under our sun's light. For a brief moment in cosmic time, this visitor from the thick disk became visible. 20 spacecraft watched. We wrote it down. We calculated the odds. We measured the carbon dioxide. We tracked the jets. We captured the images. And then NASA held a briefing and said, "Comet, no hype, just cosmos." That's the story. That's the data. That's what happened when an object older than the solar system crossed our path, and we pointed everything we had at it. November 19th, 2025. The briefing that came after the silence. The images that came after the government shutdown. The data that confirmed what we knew and revealed what we didn't. 3I Atlas. Interstellar visitor. Ancient wanderer. Natural comet. Confirmed. Measured. Departing. Gone soon. But not forgotten. Because we have the data. We have the observations. We have the images. And we have the questions that the data couldn't answer. The ones that persist. The ones that make us keep watching the sky. Waiting for the next visitor. The next object from beyond. The next chance to see something that formed around a star we'll never visit. That's the mission. That's the work. That's what 20 spacecraft and dozens of observatories and hundreds of scientists spent months doing. Tracking one comet, one ancient icy body, one messenger from deep galactic time and asking, "What are you? Where are you from? What do you tell us about the universe before our sun existed?" The briefing gave answers. Natural, comet, ancient, carbon dioxide rich, thick disk origin, 7 to 14 billion years old, single body, sunward jets. Complex tail, high non-gravitational acceleration, unusual polarization, nickel vapor, cyanide gas, 16-hour variability, million-kilometer jets, survived perihelion, currently outbound, observable until mid-2026, then gone. That's the briefing, that's the data. That's 3i Atlas without the hype, just measurements, just observations. Just what we saw when something from another star system passed through ours, and we were ready with cameras pointed at Mars and telescopes locked on target and spacecraft positioned across the solar system to catch every angle. Multi-mission campaign, 20 assets, dozens of observations, hundreds of scientists, one comet, now departing. Data archived, questions remaining. Next visitor? Unknown, but we'll be watching.